Hello guys, welcome to Self-Help Maths Academy. Today I'm going to discuss about the boundedness in real numbers. Okay, so let's understand what is the boundedness in the real numbers. What is the bound, like upper bound, what is lower bound, when do we say that given set is bounded below, above, and those discussions will be done now. Okay, so to understand, let us start with the upper bound. Okay, so to define, let S be a subset. So to understand it better, let S be a subset of a real number. Okay, it's a subset of a real number. Then it is said to be bounded above if there exists a real number k such that x is less than or equal to that real number k. This is true for every x belongs to x. Then we call the k is upper bound. K is called as upper bound of S. What do you mean by this? What is the meaning of this particular definition? So to say that the given subset of, I'll consider an example. Let me take the example to understand it better. If I have a subset, say A is a subset of R, I'm defining in such a way that my A is 1, 2, 3, 4 and 5. So this is my subset. This is a subset of a real number. Here I have a number called 5 in such a way that every element in this set is less than or equal to this 5. If I take 1, which is less than 5, 2 less than 5, 3 less than 5, 4 less than 5, 5 itself is less than or equal to 5. That means there is a number 5 such that this 5 belongs to A, such that every element from the set, if I take any element from the set A, such that every element is less than or equal to that 5. Then if this particular definition says that if this condition follows, then we call 5 as an upper bound. This is called as an upper bound of the set S. The set here, in this case, it is the upper bound of the set A. Okay. Now similarly, you can ask me that is it possible to have this upper bound for every given set? Likewise, if you see, if I consider, say, this 6, this is a given set. Here, if I take 6, which is not belongs to the set A, but any number which is greater than this 5 will be still an upper bound of this given set A. So it means the upper bounds may or may not be belongs to the given set. Okay, for example, if you see, as I'm telling you, 6, you name 6 which is greater than this 5, it is still an upper bound of A. You say 7 which is greater than this 5, it is still an upper bound of A, because it follows all the conditions of this element. Because K is not, there is no condition on a K that it is from that set. There exists a real number. It is a real number. It is any real number such that it is less than or equal to each and every element of this. So then we call that number as the upper bound of a given set. Okay. Then if similarly for a lower bound, let me define both and then we will take the examples one by one. Similarly, here S be, in this second case, let S be a subset of R. Okay. And it is said to be bounded below. We say that it is bounded below. Then there exists a real number, say small k, such that your x is greater than or equal to small k. This is true for every x coming from the given set S. Okay. Then we call that k, small k, as the lower bond. Lower bond. Let us take the same example, same very example. Here I have an element size like 1. This 1 is less than or equal to each and every element here. 1 is less than 2, 1 is less than 3, 1 is less than 4, 1 is less than 5, and so on. So 1 is less than or equal to each and every element in the given set. So therefore, here 1 will be the lower bound of the given set. So the lower bound of given set, like as I told you, so any number which is less than 1, if I take 0, 0 is still a lower bound of this given set, because 0 is less than or equal to each and every element of the set. Negative 1, yes, it is a lower bound of this given set, because it is negative 1 is less than or equal to 1. Likewise, so it's a real number which is less than or equal to each and every element of the given set. Okay, so now let us try to take our examples and understand it better. Okay, so here what happens? The set S is said to be again bounded if it has both bounded above as well as bounded below. If it is having a upper bound, then we say that the given set is bounded above, and if the set is having lower bound, we say that the given set is bounded below. So if it is having both upper and lower bound, then we say the given set is bounded. Hence, when a set S is bounded, there exist two real numbers, say small k and capital K, such that your elements from the given sets are lie between those two elements. This is true for every element from the given set. Then we call that set as a bounded set. Okay. Now let's see some examples we will take look into. The set N, that is a natural number set. This is bounded below. You can see there is a number 1 which is having, you can see this is a number which is less than or equal to each and every element. You take 100, 1000, whatever the number you quote, that will be less than or equal to 1. So hence this one will be the lower bound of the given set N. But you can see that there is no such a big number here which is less than or equal to any number of this particular number. So therefore, which is greater than or equal to, I can say. So here this clearly this particular natural number set is not bounded above. So it is just bounded below. So that means there are sets which may be bounded below but not above. There are sets which are bounded above but not below. And there are sets which are bounded both above as well as below. So that should be the very important point to be noted. Now let's see this set. The set 1, 2, 2 square, 2 cube, and so on. This set is again bounded below by the number 1, but it is not bounded above. Okay, now let's see this the given set log of 1 over n, where n is a natural number set. This if you take the values, it is having the numbers in such a way that this set collection will be bounded above. It has the upper bound, but it is not bounded below. It has no least number. Okay, so therefore, as this particular set is clearly bounded above but not bounded below. And here very important property, as we know what is a finite set in the last class. So every finite set is bounded. So as I told you here, if I take the example of the one which we discussed, if you take A is equal to 1, 2, 3, 4, 5, this is a finite set which contains 5 elements. It is both having a lower bound as well as the upper bound. Hence, this set is bounded. So in general, every finite set is bounded. Okay, very important property. Then each of the intervals, if you see the closed interval where the endpoints are included, the open intervals where it includes every point except the last, you can see the last entry A and B. And this is semi-open, which includes A but excludes B. Semi-closed, which includes A, which excludes A but includes B. Is all these sets are bounded sets. So it is all having the lower as well as upper bounds. Okay. Then if you see this set 1 by 2 up to 1 by 6. So this is having the 1 by 6 as the lower bound and 1 as the upper bound. So therefore this particular collection is a bounded set. And similarly, if you see each of the sets like integer sets or set of rationals or set of real numbers, they are actually the real, the rationals, they are neither bounded below nor bounded above. Okay, so therefore it is important to understand how the bounded sets works. All right. Okay, now let us talk about which is important, that is supremum. Okay, or also called as least upper bound. It is also called as least upper bound, LUB. So we know that if S be a subset of your real number, and S is say bounded above. If S is bounded above, okay, then there exists, when I say bounded above, that there exists element K such that every X is less than or equal to K. This is true for every X belongs to that given set. This we know. And I also told you any number which is greater than K is an upper bound of given set. Like that, there are infinitely many numbers which will be an upper bound of a given set S. So there are infinitely many numbers which will become the upper bounds of a given set S, because K is any real number, that has to be noted. Okay, but out of all the upper bonds, okay, out of all the upper bonds, like as I told you, like every number which is greater than this K will become an upper bond. Out of all this upper bonds of a set S, the smallest upper bond will be this K. The smallest among all the upper bonds will be this K. That's why this K is called as least upper bond. This K is called as least upper bond. So in a given set A, if I take 1, 2, 3, 4, 5, 6, and here I told you that 6 is the upper bond. In this case, if 6 is the upper bond of a given set, and I also told you any number which is greater than 6 will be an upper bond of a given set. So if I take 6 is upper bond 7, upper bond 10, upper bond 11, upper bond 100, upper bond. Likewise, there are infinitely many upper bonds. But among all these upper bonds, 6 is the smallest number which is upper bound of this given set. So there is no less, smaller number than 6 which is an upper bond. Hence 6 will become a smallest one. So this is, since it is the smallest and unique, there is no such number which is less than 6 will become an upper bond. Hence this is called least upper bond. Least upper bond, or it is also called as supremum. This is called as supremum. Okay, so this is very important. So supremum is basically in mathematical entity, the property of the supremum is, the first property is, say X is less than or equal to, if I take S, supremum yes, supremum is, say yes is my supremum, then X is less than or equal to each and every element, every element is less than or equal to that S. Okay, this is true for every X belongs to S. Thus we know that is S will be an upper bond. That is the first condition. Second condition is, for given epsilon greater than 0, say however small, okay, however small, there exists, say Y belongs to the given set, Y belongs to the set S, such that your Y is greater than S minus epsilon. So that means if I take S as the upper bond, okay, so you choose any epsilon greater than 0, okay, then your S minus, and also you take any element Y belongs to S such that Y will be still greater than that S minus epsilon, means S is the least one. So there is no such number which is lesser than S will become an upper bond. That is the meaning, okay? And that is very important, two properties which we need to know. To become a supremum, first it has to be upper bond and it has to be a least one. So that those two are the conditions on the supremum. Similarly, for an infimum, what happens here, what we for a given set, yes, if S is, say, bounded below, when I say bounded below, when you say bounded below, it is important that it admits that there are infinite numbers which are less than this element, that is the lower bond. For example, as I told you, there is a lower bond K such that your X is greater than or equal to this K. This is true for every X belongs to S. Then your K is becoming a lower bond, right? So what I'm trying to tell you is, so here any element which is less than K will be still a lower bond. Okay. So that means less than a lower bond is also a lower bond. So if the set of all lower bonds, if the set of all lower bonds of the set S has a greatest member, then we say that this is the greatest among them. Hello. It is the greatest among all this. Okay. So hence we call K as greatest lower bond. This is a greatest lower bond. For example, in this case, if you see, your 1 is the least bond. Okay. So least upper bond. So here any number which is less than 1, 0 is also a least upper bond. If I take negative 1, this is the least upper bond. Negative 2, it is also lower bond. So 0 is a lower bond, negative 1 is a lower bond, and negative 2 is a lower bond. But which one is the greatest among them? 1 is the greatest among them. So that's why it is called as greatest lower bond. Okay. So that is very important. So here also for an infimum, as you see, if your T is an infimum, then it should be first lower bond. That is, T should be less than or equal to each element. This is true for every X belongs to X. That is first property, that it need to be a lower bond first. Then for a given epsilon greater than 0, however small, there exists Y is coming from the given set such that your Y should be less than T plus epsilon. Means your T must be the greatest among all the elements. So any element you choose, that should be less than the the chosen element. So therefore, what is important is, first is it has to be a lower bond, then it has to be greatest among all the lower bonds. All right. Then we call that as the supremum as well as infimum in general. So now let's see some of the examples. Okay. Now the infimum has the following properties. As I told you, I've discussed them. Now let us see some examples. Let A is equal to say 3, 4, 7. In this we have got the upper bond as 7 and the lower bond is 3. So the least among all the upper bonds is 7. That is supremum, which is belongs to the given set. And the greatest among all the lower bond is 3. So therefore 3 is the infimum. So in this case, both infimum as well as supremum is a part of a given set. So now let us consider this set. Let A is equal to 1, 1 by 2 and so on. This is nothing but it is 1 over n. N is coming from the natural number set. So here 1 is the element. This is bonded above. Okay. So therefore if you see, this is bonded above, and it's like as n tends to infinity, this goes to 0. So therefore it is bonded below by 0. So 0 will become a lower bond of this set, whereas this given set 1, the 1 will be the upper bond of this set. And not only 1 as the upper bond, so therefore 1 is the least among all the upper bonds. Hence the supremum of this given set is what? 1. Similarly, this is it actually goes to 0. Any number less than 0 will still be the lower bond, but 0 being not included in the given set, but still it will be an infimum of given set. That means the supremum and infimum may or may not belong to the given set. Here the infimum of the given set is not belongs to the given set. Okay. So now for an open interval like this, you have an open interval, say C is equal to open interval 2, 3. So here supremum of this is 3 and infimum of the given set is 2. Here both infimum as well as supremum, both are not included. As you know, it is an open interval. So the endpoints are not included. So it has a supremum, it has the infimum, but it is not included in the given set. Okay. So like this is these are the examples where we can say that the supremum and infimum are not a part of a given set. All right. Now next proof we will see. Prove that every finite set is bounded, and we have to prove every subset of a bonded set is bounded. To prove that, because we know we have seen example and we know that every finite set is a bounded set. But to prove, let us consider let A is equal to A1, A2 up to AN. So you can see here it is started from A1 to AN. It's a finite set. So let me consider, say H is a minimum of all A1 to AN. Okay, and let K be the maximum of A1 to AN. So the minimum of this A1 to AN and K is defined as maximum of A1 to AN. Then if I pick up any element, say X, among this given set, then it has to lie between that minimum as well as maximum. So therefore your X lies between the minimum of element and maximum of element, right? That means what? Your X is lying between, there is a lower element and the upper element. So this implies what? This is true for every X coming from the given set A. Hence the given set A is bounded. It's a simple proof. Similarly, now we have to prove every subset of a bounded set is also bounded. Now let A be the bounded set. Okay. Then there exist two real numbers H and K. When I say it's a bounded, means there exist two real numbers H and K such that X lies between H and K. This is true for every element X. Now what I do, I'll take a subset. Let B is a subset of A. Then Y belongs to B. When Y is an element of B, implies Y is also element of A. Because every element of B is an element of A, since your B is a subset of A. But our element of A lies between H and K. So therefore this Y being an element of A, it should lie between H and K. Since this Y is also element of B, okay, Y is an element of B, therefore every element of B are lying between H and K. Hence this is also bounded. So this implies every subset of a bounded sets are bounded. Okay, that is very important. Now let's see this one. Prove that the supremum of this is equal to half. So to start with, clearly we have this type of set where n upon 2n plus 1. The next number 1 less than that, n by 2n. This is less than 1 by 2. This is true for every n greater than or equal to 1. So this 1 by 2, if you see, 1 by 2 is the upper bound. I mean, this is the greatest number on which if you take any element which will be less than or equal to 1 by 2. Hence this has an upper bound as 1 by 2. So 1 by 2 is an upper bound of this given set. To verify that this 1 by 2 is a least upper bound, let me choose some epsilon greater than 0 arbitrarily. So let us call a set S is given by, okay, S equal to n by 2n plus 1, where n is equal to 1, 2, 3 and so on. So this is equal to say 1 by 2. That's how we defined it. So now we try to find out some S epsilon, okay, which belongs to S, such that now what I have to do to prove 1 by 2 is the least, I should try to find out the number which is greater than, the less than this 1 by 2, say 1 by 2 minus epsilon. That should become an upper bound. If that is the case, then our assumption will be wrong. So to do that, what I will do, I will try to find out some S epsilon which is coming from the given set, yes, such that 1 by 2 minus epsilon is less than S epsilon. This is less than or equal to 1 by 2. If you observe, I am choosing some number 1 by 2 minus epsilon which is less than 1 by 2, which is becoming a upper bound at C. So but SE belongs to S must be of the form this, because our each and every element is of the form n by 2n plus 1. So therefore it should be true for some positive integer n epsilon. So we must find some positive integer n such that I'm replacing now this S epsilon by how the set is defined. So 1 by 2 minus epsilon is less than n epsilon upon 2n epsilon plus 1, which is less than half. Okay, so this is what we have written. Now but n epsilon upon 2n epsilon plus 1 is less than or equal to 1 by 2. That means every element of this type is less than or equal to 1 by 2. In the first step itself we said this holds for all the positive integers. Therefore your n epsilon is greater than or equal to 1. So also we know that every element is less than or equal to itself, so holds for all the positive integer n epsilon, such that your n epsilon is greater than this number. So hence the supremum of all these numbers so is equal to half. So therefore half will become a supremum of the given set. Okay, and similarly we have got one proposition that supremum of a subset of S, supremum of a subset of S, set S, if it exists, it should be unique. Means there are no two supremum for a given set. Okay, So if the supremum exists, it should be unique. So how do we prove this particular to prove that supremum of a subset of a set, if it exists, it is unique. So let us if possible, what I'll do is, if possible, we there exist two supremums, okay? Two supremums of S, say S and S dash. Now, since S and S dash are a supremum, so S and S dash should be upper bonds. S and S dash are both upper bonds, okay? Because supremum means it should be upper bond first, upper bond of S. So since S is the for a least upper bond, because it is a supremum, S is the least upper bond, and say S dash is the upper bond, okay? So as you know, S is the least one and S dash is any upper bond. You know that every upper bond will be greater than or equal to the least upper bond. So therefore, your S is less than or equal to S dash. Let me take this as 1. Now again, what I do is, I take, let S dash is the least upper bond, S dash is the least upper bond, and S is the upper bond, okay? S is the upper bond. Now S dash is least upper bond and S is the upper bond. So therefore your S dash should be less than or equal to S. This is equation 2. So from equation 1 and 2, it is clear that S should be equal to S dash. Therefore, from 1 and 2, whatever we assumed that there are two supremums, which is wrong. So therefore, it follows that there is only one supremum. The same way, guys, we also can prove that the infimum of a subset of S, if it exists, it is unique. Okay, so that implies supremum and infimums, they are unique elements. There should be only one supremum for a given set, and there should be one infimum for a given set. That is the important note we need to understand. Okay, so this is all for in this discussion, guys. Maybe in the next video we will come up with some more properties, some more ideas on the the supremum and their properties we will see. Okay, so till then, take care, guys.